Welcome to Formal Methods Lecture 2 Recap. We will start with a property of textual substitution. And here is an example. So here we have the expression parentheses a plus b close paren times c, all enclosed in parentheses, and we have two successive textual substitutions, b replaced by x and then x replaced by b. And the question, of course, is in what order do we do this operation? And the answer is we do the b replaced by x textual substitution first on the expression, and then we do the x replaced by b on the result of that first operation. So going from left to right, the way we read in English. Okay, so the first step is textual substitution and remove unnecessary parentheses. So what do? We take a plus b close paren times c, and everywhere there's a b we replace it with x. So what do we have? Can you anticipate this before we go on to the next step? I hope you got a plus x times c, and then we bring down the textual substitution x replaced by b. And now how do we do this textual substitution and remove unnecessary parentheses? Well, everywhere there's an x, you take a plus x times c, and everywhere there is an x, you replace it with b. So the result of this is a plus b times c. Now, what do you notice about this a plus b times c? It's the same as the original expression, which kind of makes sense, doesn't it? Because what does the original expression say? It says we take this a plus b times c, and first, everywhere there is a b, we replace it with x, and then after that, everywhere there is an x, we replace it with b. So it seems like if you're going to replace b with x, and then x, you're turning all the b's into x's, and then you're turning all the x's back into b's, why wouldn't it be the same? Indeed. But it might not be, as shown in this example. In this example, we have the same, well, we don't have the same expression. We have a plus b times x. And then we have the textual substitution first, b replaced by x, and then after that we do x replaced by b. Now, what are the steps in this example going to be? Well, first step, textual substitution and remove unnecessary parentheses. And everywhere there is a b, we replace it with x. So, do you see what's going to happen in the next step? It's going to be a plus x times x, and then on that we have to do textual substitution x replaced by b. And now when we do that, the second textual substitution and remove unnecessary parentheses, everywhere there is an x, we replace it with b. But now there are two x's in the expression, and so everywhere there is an x, we have to replace it with b. So what do we wind up with? What do you think the next line is going to be? I hope you said a plus b times b. Now, is this the same as the original expression? And it's not, because the original expression was a plus b times x. So you see, it's not necessarily the case that if you have an expression that has a b's in it, and everywhere there is a b, you replace it with x first, and then after that, everywhere there is an x, you replace it with b, you will not necessarily get the same as the original expression. So the question is, when do you get the same as the original expression, and when do you not? What was the fly in the ointment in this second example that caused the final expression to not be the same as the original expression? Well, look, the problem was that the original expression contained an x in it. And so in the second step, there were two x's, and both of those x's got replaced with b, so that was not the same as the original. So here's my question. Under what circumstances is it the case that if you have an expression, and everywhere there's a b, you replace it with x, and everywhere there's an x, you replace it with b, under what circumstances will you get the same as the original expression? What has to not happen? What happened in the second example that was not the same in the first example? The problem was that little extra x in there. So do you see that the original expression contained an x? In other words, x occurred in the original expression. And if x occurs in the original, because x occurs in the original expression, that means that when you take that expression and everywhere there's a b, you replace it with x, followed by everywhere there's an x, you replace it with b, that will not be the same as the original. So here, but on the other hand, if that x did not occur in the original expression, then what you're going to get is the same. So we can encapsulate all of this into this rule. Now here we are using this occurs predicate. It's a function that returns type Boolean. That's what a predicate is. And you see that little symbol in front of the occurs, the horizontal line with a little downward notch on the end of it. The way you pronounce that is not. So literally, the way you would pronounce this, literally you would say if not occurs x in E. Or just rearranging the English words, you can say if variable x does not occur in expression E. So as long as x does not occur in E, then if you take that expression E, and everywhere there is a y, you replace it by x, followed by everywhere there is an x, you replace it by y, you are going to get that same expression E back again. So E with y replaced by x, followed by x replaced by y equals E. But that only happens if the variable x does not occur in expression E. Okay, next topic is proofs. Now this material is not in the lecture, and I think this is going to be some additional information that you will find useful as we continue on in this course. So what is a proof? We're going to do lots of proofs in this course in formal methods. In fact, it's practically all of it is proofs. And I want to show you an analogy with a computational system. Now most people who are taking this course are taking it because it has direct application to programming. So what is a program? What does a program do? Well, a program processes information. And all programs do one thing. Well, actually they do three things. They take input, like in C, C++, you have cin. Okay, so the program which does the processing takes input, it processes it, and it produces output. As an example, suppose the input is a file of numbers that are in some random order, and suppose that the program which does the processing implements a sorting algorithm that puts them in order, and then the output would be those same values from the input except in alphabetic order or in numeric order. So that's what a program does. A program takes input, processes it, and produces output. And as programmers, we can understand this operation, this system. Now, there is a direct analogy to proofs. So here we're summarizing the programming analogy. Given a program and its input, the program produces the output. You can think of it as the processing takes the input and generates the output. Now, look, it's exactly the same thing with axiomatic logic systems. So, and what we are constructing here in this formal methods course is an axiomatic logic system. So here's what an axiomatic logic system does. What it does, in the same way that a program takes input, processes it, and produces output, an axiomatic logic system takes axioms and uses what is called an inference rule. And the inference rule takes the axioms, and the inference rules produces theorems. In the same way that a program takes the input and produces output, axiomatic logic systems take axioms and use inference rules to produce theorems. And we're going to talk about this in more detail later, but this is the general idea. So you can think of an inference rule as kind of like a program that transforms axioms into theorems. All right. And so here is the description. Given the inference rules and some axioms, the logic system produces theorems. So that's the idea of an axiomatic logic system, and this is our introduction to the concept of what an inference rule is. Okay, now these axioms are going to be expressions, and theorems are also going to be expressions. And the axioms are going to be expressions that we assume that they are true in all states. And the inference rules are going to produce theorems that are also true in all states, but they are going to depend on the axioms, and the inference rules produce them. So the inference rules take axioms as input and produces theorems, and the inference rules produce theorems as the output. So there's this analogy to programming systems. All right, so now the question is, what is an inference rule? So inference rules. First, an inference rule has a horizontal line. Isn't that a nice horizontal line? Okay, and what goes on the top of the line? The premise or the hypothesis which is assumed to be true in all states. Then below the horizontal line is the conclusion. Okay, and so that's what an inference rule is. We'll give us some examples here in a minute. Now there are 4 inference rules for logic proofs. Now we're going to display some of these right now, and we'll have to wait till we will discuss some of them now, but some of them we will wait till a later lecture. But these are the 4 inference rules for logic proofs. This material that I'm summarizing for you here is not that systematically presented, I think, in our textbook. So what are these 4 inference rules? The first one is called substitution. Now notice that because it's an inference rule, it has a horizontal line. And what's on the top of the line? The hypothesis that is assumed to be true in all states. So what is that capital E? That capital E is an expression. And then below the line is the conclusion. So the way substitution works is, if E is true in all states, if you assume that E is true in all states, then the conclusion is that E is true for any variable inside E replaced by any other expression F. Okay, so this E is an expression. It could be, it could have some unary prefix operators, some parentheses, some binary infix operators, and some constants and some variables. And one of those variables might be the variable Z. And if E does have Z in it, then that E with Z replaced by F is textual substitution. So that's our substitution inference rule. There's 4 of them. The second inference rule is called Leibniz. Now this is the correct German pronunciation. It's not Leibniz, it's Leibniz. So EI is always pronounced I in German, in the German language. So Leibniz says, if x equals y in all states, then any expression with z replaced by x is equal to that same expression with z replaced by y. So that's the second inference rule. The third inference rule is called equanimity. And what equanimity says is that if x is true, and if x equals y, then y is true. If x is true in all states, that comma means and. So let me restate that. If x is true in all states and x equals y is true in all states, then the conclusion is that y must be true. And the last inference rule is transitivity. And the transitivity inference rule says that if x equals y and if y equals z, then x has to equal z. So these are the 4 inference rules for logic proofs. What we're going to do now is I'm going to give you an example for the substitution rule, and we will show you how the other rules work in later lectures. Okay, so here's our substitution example. So we have the horizontal line as usual with inference rules, and on the top of the horizontal line we have this expression x squared is greater than or equal to 0. And then below the horizontal line for the conclusion we have the same expression x squared is greater than or equal to 0, and then we have textual substitution x replaced by b plus 3. So now how is it that this is an example of the general substitution rule at the top of the slide here? Well, we can see that the expression E is x squared is greater than or equal to 0. Obviously that greater than or equal to 0 is obviously that greater than or equal to operation is a binary infix operation, binary infix operator. And then you see the E that is on the top of the horizontal line is the same E below the horizontal line. So that same expression, x squared is greater than or equal to 0, is at the bottom is below the horizontal line. And then the next correspondence is in the general rule where we have z. In this particular example, the variable is x. And then in the general substitution rule where we have the expression f, capital F. Remember, uppercase letters are expressions and lowercase letters are variables. Our expression f is b plus 3, where obviously the plus is a binary infix operator, b is a variable, and 3 is a constant. And so what is this saying? Why is this statement true? Well, what happens if you take x squared, what happens below the horizontal line if you take x squared greater than or equal to 0, and everywhere there is an x you replace it with the expression b plus 3? Well, here's what you get. You get parentheses b plus 3 quantity squared is greater than or equal to 0. So what is this substitution inference rule telling us? It's telling us that if you assume that x squared is greater than or equal to 0 is true in all states, then the quantity b plus 3 quantity squared is greater than or equal to 0 in all states. So this is something that you learned in algebra. Here again, it was not presented this explicitly and in this format, but it makes sense. It's something that you are already familiar with, but what we are doing now here is we are formalizing it, which is why this topic is called formal methods. We are formalizing our logic. Okay, so that concludes the Lecture 2 Formal Methods recap. See you next time.